it will rise. How fast is it going to rise? Every minute it will rise by how much?
2
liters.
Every minute will rise by 2. That's the difference between the 12 and the 10. So this guy needs to be replaced by 1,000 plus 2t. Is it okay?
Yeah.
You guys good?
Yep.
What happened if I change this to 7 instead?
Minus 3t.
This will be minus, this will be 1,000 minus 3t. And this will change to over here.
7.
This will change to 7. So I hope you guys understand this. So that is some variation, right? So this guy is still linear though. The equation is like this red one here. It's no longer separable, but it's still linear. You can use integrating factor to solve it. Do you guys want me to solve some of this, or you want me to just keep talking about variation of this type of problem? Can I just talk about variation without solving this?
Sure.
It's another variation. Back to the original one. 10 liters per minute. Okay. Except that in this case, there's a valve there. Okay. You can have, so it is 10 liter per minute, but the concentration depends on whether it's the top or bottom are going to be different. And you have this valve here. This valve can flip from one side to the other one. Okay. Let's say this is 0.2 kilogram per liter, and this one is 0.4 kilogram per liter. So initially, also Y0, okay? Initially Y0 is equal to 50. Now, this is valve A. Valve B.
Okay.
So initially, valve A is open, B closed. Let's say at time t equal to 5, valve A is closed and B open. Let's see what we do. This is more complicated now. Okay? You suddenly switch the valve. Do you guys understand the setting?
For valve B, is it also 10 liters per minute?
Yeah, it's also 10 liters per
Okay,
minute.
thank you.
Yeah, otherwise it's going to be a little bit too complicated. It's still probably, you can set it up, but solving is going to be much harder, a lot harder. Okay, so does the water level change?
No.
Water level is not going to change. So we will set this out. 10 times something minus 10 times y over y over 1000. It's just that this thing here is going to be troublesome, right? What is in here? Okay, this is some function of time. Okay, this guy is just some function of time. What is that function of time? That function of time is going to be at the beginning is 0.2, and then later on is 0.4. Do you guys understand what I'm doing?
Yes.
Now, to solve this in a concise manner, we are going to use the step function. You need to write this guy as some type of step function. At the beginning, so this guy, if I grab it, okay, I don't think you guys like the graphs. I'm going to do it like this. At the beginning, okay, it's 0.2. Later on, it's 0.4. So if I want have, what's the best way to say this? So you want this guy to be equal to 0.2 times some function plus 0.4 times some other function. Okay? This function, this function here, I want it to have this property. Over here, this function here, I want it to have this property. Do you guys agree?
Sounds good.
Yeah,
Other people okay?
Yeah.
Does it sound good?
Yeah.
Makes sense.
Okay. I want this type of function. What function will have this property? What function will have this property? What function will have this property? The green one is actually easier because it's 0 at the beginning, right? And later on change to 1 at t equal to 5. So this guy is actually ut minus 5. Yes?
Yeah.
What do you think this guy is?
1 minus u of t minus 5.
Yes. Is it okay? Is it all right?
Yeah.
Okay. So this guy equal to 10 times ft. This is my ft. 0.2 1 minus u t minus 5 minus plus 0.4 u t minus 5 and then minus y over 100. This guy can be simplified. N times how many ut minus 5? Positive 0.4, negative 0.2, right? So it's 0.2 this term plus and you can use Laplace transform to solve this. Is it okay? So that's another variation. I'm not going to solve this with Laplace transform. I'm assuming you know how to do this. Okay? Just take the Laplace transform on both sides and so on. And keep going. Okay? Yes?
Yeah.
I am going to do another variation. Maybe you guys can help me. I have two tanks here. 10A and 10B. Okay? And let's say this going in 10 liter per minute. Okay? Coming out here, okay, it's 12 liter per minute. This guy going in here is also 10 liter per minute. But there's a path where you pump this guy, pump the output of this guy back into here, 2 liter per minute. Okay? Then we have, let's say originally, this is 1000 liter. Originally, this is 500 liter. So AT will be amount of salt in tank A at time t. Then BT, maybe I call that X and Y then, okay? I call this XT then, and this is YT. Amount of salt at tank B at time t. And initially, I'm going to just make something up. You guys know what I'm doing? So now I have two functions of time. So what I'm going to set up is actually a system of equation. Does the water level in 10A change?
It doesn't change.
It doesn't change. Because you have 10 going in and then the 2 coming in and 12 going out. It's 12 in and 12 out. How about B?
Doesn't change.
Doesn't change. Okay. Now let's set up the differential equation. Oh, I need to tell you the concentration here. Coming in. 0.4 kilogram per liter. Okay, let's set up the equation. So what will be dx dt? Can you guys help me? Is the stuff coming in, subtract the stuff going out. The stuff coming in is this one. Here. One place where it come in. How much is that? 10 times
0.4.
10 times 0.4. Now there's another one coming in. So it's plus 2 times what?
Y of t.
Y of t divided by
500.
divided by 500. That's the concentration. Very good. Very good, John. Subtract what? Subtract. This is
12
coming out.
times x over 1000.
12 times x over 1000. How about dy dt? Coming in is 12. 12 times what? Is this guy. Okay. This arrow is for this going out and this coming in, right? These two the same. 12 coming in. How much going out? 12 going out. Oh my God, this arrow should be drawn a little bit lower. Otherwise, it's just pumping air out there. Okay. Okay. So, okay. So subtract what? All these are same concentration going out, right? So I can merge these two together. Is it okay? So I set this up. And we actually have learned how to solve this. I'm not going to go through it's a little bit clumsy. I mean, it's very tedious, but we have learned how to solve system of equations, 2 equations, right? Okay, both first order. We use differential operator to try to cancel some terms, and then end up with a second order equation, and then take it from there. Do you guys understand how to set this up?
For dx dt, where it says plus 2 times y over 500, why would it be 500 and not 1,000 if it's going back into the A pool?
But it come from the B pool.
Oh, okay.
It come from this guy.
Okay, thank you.
Yeah. So that is the concentration. It's just this stuff going out. So, any other topic you want me to reveal?
Spring dampening, or any stuff like that.
Oh, I see. Okay.
Wait, Professor, could I say that for one last second? Okay.
No problem. Spring damping. Okay. Mass times acceleration. Okay, it looks like this. Okay. So the way that our book do this is positive direction. Okay. So x is the displacement from equilibrium position. Okay. Mass times acceleration equal to the force. Okay. The force, there are two parts. There are two parts. I forgot the terminology. I forgot what symbol they use. So I have to take a look what symbol they use. Okay. One is the one is the spring constant. Okay, K. But it's going in the other direction because if you pull it down, it's going back. Okay. The other one, so the other one is the damping constant. So this is the spring constant. The other one is the damping constant. So beta is the damping constant. Okay. So we can rearrange this a little bit. Will be mx double prime plus beta x prime plus kx. Okay. Now at the beginning, we are going to just talk about 0 for the other side. 0, that means there's no external driving force. We are not moving the support here to drive it. Just this support is constant. Later on, we can change this. If you're holding this support and then just moving your hand, then that will be different. Okay. Of course, you have the initial condition. Okay. Do you guys understand what this means? This is the initial position and the initial velocity. Initial position means that where do you release it? Okay, what is this position relative to the equilibrium position at time t equal to 0? And here is when you release it, do you push it up or down? Okay, it would be this condition. So this guy would divide this by, we divide this by m. Okay. And we use these symbols. Okay. So basically, this guy is going to be 2 lambda. You don't have to call it 2 lambda, but our book call it 2 lambda to make all this stuff a little bit easier to see. Okay. The reason this is omega square is the following. So omega is basically the angular velocity when this is simple harmonic motion. It's because of this. Okay. When you have this, when there's no damping, this is no damping. No damping is simple harmonic motion. Okay? It's simple harmonic motion. That means the spring will just keep bouncing back and forth. Okay, the answer will be sine and cosine. So just take an example, x double prime plus 9x equal to 0. What will be the auxiliary equation? M squared plus 9 equal to 0. What will be M? What will be M? What are the roots of this guy? Can you guys solve this? Yes? Can you see
3i.
3i plus or minus 3i? Plus or minus 3i, we know that the solution is going to be x cosine. It's going to be x equal to c1 cosine 3t, c2 sine 3t. Okay. So this 3 here is called the angular velocity. Okay, and they usually denote by omega. So this omega is actually 3. Where does the 3 come from? It's the square root of 9. Okay, what is the 9? The 9 is k over m. So you can probably see that this omega is actually square root of k over m, right? Can you see that? Can you see that? If I change this to 16, if I change this guy to 16, I will have cosine 40, right? Sine 40. Yes? What happens if I change this to 25? What would this be?
5.
5.
It would be 5. So it's always the square root of this. So the angular velocity is the square root of this. And this guy is the angular velocity. Okay? And that's why they write as omega squared. Okay? So this is the equation now. This is the equation. And then you have many different cases, depending on whether it's over damped, under damped, or critically damped. Okay? So we have two choices here. One is for me to start to plug in some number and demonstrate to you which case which. The other one is going to be I just continue to operate with these symbols. And then we have these expressions. What do you like? Symbols or numbers? Symbols or numbers?
I'm a fan of symbols.
Okay. So since no other people are responding, we're going to do symbols. Okay. Number of cases. Case 1. Now you need to understand that what we have is the auxiliary equation. It's going to be m squared plus 2 lambda m plus omega squared equal to 0. Then you solve for m. You solve for m will be quadratic formula minus 2 lambda plus or minus square root b squared minus 4ac, 4 lambda squared minus 4 omega squared, all over 2a. Take the 4 out here. Take the 4 out from here. Become a 2 outside. Cancel with this 2. So we end up with this. So we have different cases now that we need to talk about. Case 1, okay. Case 1 is the case where case 1 is lambda squared minus omega squared bigger than 0. Bigger than 0. So this one is, would that be complex number then for the m? if this guy is bigger than 0, this guy is bigger than 0, do we end up with complex numbers?
No.
No, no complex number. Complex number will need to sine and cosine, right? Without the complex number, it will be just exponential. Okay? You guys know what I'm talking about? It will be just exponential. So this is the case where you enter, the answer is going to be some exponential stuff, okay? And this exponential stuff will, this is called the overdamped case. I'll show you the exponential function on the next page, okay? I just want to talk about the 3 different cases, okay? Overdamped means that it will provide enough resistance that it's not going to just bounce forever, okay? It bounces around a little bit and then it will stop bouncing. It doesn't bounce forever, okay? I'll go with the, I'll write out the detail for this. What do you think happened here? When this is equal to 0, you still have 2 solutions. Can you see those 2 solutions overlap? Because it's minus lambda plus or minus 0. Okay, I'm going to talk about that more in the next page then, okay? So this is called critically damped. And case 3, this is less than 0. When that guy is less than 0, what happened?
Complex number.
Complex number? The complex number will need to this sine and cosine, which is going to keep bouncing. But the amplitude gets smaller and smaller, but it still keep bouncing. Okay? So this is called underdamped. So you don't, underdamped means that you don't have enough resistance or damping to cause it to just die down right away after a short time. It will keep bouncing forever. So we will write out the solution for case 1, case 2, and case 3. So I'm just rewriting some of this here on this page. Okay? We just solve all this stuff in terms of symbols. What will be my M? There are 2 of them. One of them is this. The other one is this. Now, make sure you understand these are real numbers. Okay? This is real. Are we okay?
Yeah.
So, these are real numbers, and they're different. So, xt will be C1, okay? E to the power of this guy okay? So that will be the answer. You can determine C1 and C2 by putting in the initial condition. Okay? What I'm trying to say is here is that the picture is going to look like that. Okay? Depends on where you start and so on. Okay? So it either immediately go down and just approach zero. Okay? It can potentially go up and then approach zero. Okay? It can go down a little bit, go and then go back and approach zero. Okay? So this is the situation in this type of solution. Okay? In this type of solution. Basically what happened is that, I think there's probably a fourth one. If you push it a little bit but not too hard, okay, it will look like the other one. Very similar to this other one. Okay. Okay, maybe I don't have the dotted line. The dotted line one is really just this one. They're similar. So those are the three. So basically what happened is that it's not going to go down, come back up, going down, up, up, up. So basically what happened is that it crosses the x-axis at most once. Okay, it crosses the x-axis at most once. That means it cannot be just a sinusoid keep bouncing. How do we know that? How do we know that? We can actually show it. Okay, by doing the following. What does crossing the x-axis mean in terms of this equation? Crossing the x-axis, sorry, it shouldn't call x-axis, t-axis, the horizontal axis. You guys know what I'm talking about? I'm sorry I messed up this notation. The t-axis. That means you can only cross the equilibrium position once. How do I find the time when it does? How do I find this time? This time here. How do I find it? Based on this equation. Setting something equal to 0. And solve for t. Are we lost?
I don't think we're lost. We're just taking notes.
Okay. So what I'm trying to claim, here's my claim. It crosses the t-axis at most once, the horizontal axis. That means it never just keep bouncing it back and forth. And I can actually show that by set x equal to 0 and solve for t. And see how many solutions are there. Okay? So I'm going to go ahead and do that. I'm setting x of t equal to 0. Now remember this C1 and C2 are some numbers depending on the initial condition. How do I solve this equation for t? You have any suggestion? How do we solve this equation for t?
Take the natural log of both sides.
Say it again.
Take the natural log of both sides.
Yeah, take the natural log. Before that, I have to move one term to the other side first, right? Otherwise, you'll have log of this sum.
Sounds good.
Okay. So can I just do that? Can I move one term to the other side? I just move one term to the other side. And then I can essentially take the log. Okay. Or I can actually, essentially you can take the log now. Okay, it will work. Okay. Or I can do it slightly later, which will also work. I'm going to do it slightly later. Okay, so minus, this will be, I'm going to do this. I'm gonna write out, not being so lazy. Minus lambda plus lambda squared minus lambda squared t divided by You guys agree with this?
Yep.
Then I can combine these exponents, right? Can you see those exponents as such subtraction? E to the power something divided by e to the power some other thing is e to the power something minus some other thing.
Yeah.
Is it okay?
Yeah.
Yeah.
So so when you do the subtraction, the minus lambda cancel. You have two copies of this. Then you can take log. So that is my t. So I either get one answer or no answer. When will I get no answer? It's when this guy depends on that guy, right? Ln, okay. If this guy is less than, if this guy is negative, I definitely won't have any answer to this equation. This Ln is undefined. What happens if this guy is negative? Then I have a problem. Okay. That doesn't work. This is C. Sorry, this is a 1 here, down there is a 2. So if this guy is negative or 0, I have a problem. Okay. So when this guy is a positive number, okay, but less than 1, it also doesn't work. If this guy is positive but less than 1, then I end up with negative number. Then t will be negative. So I need this guy to be this equal would not, so Ln1 is 0. Okay. This is okay. So this one will be, what I need is bigger than equal to 1. So this one will work. Then we will have one answer. So what I'm trying to say is that you cross the x-axis at most ones. Okay? I will just have enough time to do the other 2 cases. So any questions so far? So this is basically saying that, okay, I'm trying to claim that it crosses the t-axis at most ones. Okay, I'm talking about for t bigger than equal to 0. Okay, so and I demonstrate that. So it can really bounce back and forth, back and forth. So case 2. Case 2 is lambda squared minus omega squared equal to 0. Then your m will be minus lambda plus or minus 0. That means m is equal to minus lambda and minus lambda. So how does the equation look like? So x of t will be c1 e to the power minus lambda t plus c2 e to the power minus lambda t. But these were the same. What happened? You can't have the same one. These two are not linearly independent. You guys remember what happened when you double root? You know.
The T in front of one of the E's.
Yeah.
Thank you. Put the T in front of it. And the picture for this looks very much the same as this. Sorry. Look very much the same as this. Okay? It also crosses the t-axis at most ones. This one is even easier to see because you set this guy to 0. You set this guy to 0. This is common factor. Always positive is gone. 0 is c1 plus c2t. T is equal to negative c1 over c2. So it depends on this guy. Once again. And c1, c2 depends on the initial condition. So this case is called critically damped. It's called critically damped. Okay. Over damped. The first one over damped. Second one critically damped. The third one under damped. So the over damped and critically damped are essentially the same thing. Very similar, except the equation look a little bit different. Basically, it's an exponential decay. Case 3, lambda squared minus omega squared, less than 0. In this case, m is going to be, m is this, right? Minus lambda plus or minus square root. But this guy is going to be, okay. But this guy is negative, right? This guy is negative. So I'm going to rewrite this as this. So that now this one is positive now. If this one is negative, you flip it, become positive and put an I here. Are we okay? So what is the answer? xt is, you guys remember that answer? Those answers? Alpha plus beta I. Alpha plus or minus beta I is going to lead you to e to the power alpha t cosine beta t plus e to the power alpha t sine beta t, right? Do you guys remember that? Coming back to you. So I'm just applying that to here. Okay? E to the power minus lambda t. This is C1 here. Cosine how many t? Cosine this guy. Cosine this guy. Plus C2 e to the power minus lambda t. Sine this guy. Is it okay? You guys still following? these guys can be taken the e to the power minus lambda t out. Then you have C1 cosine this plus C2 sine this guy. Now, once again, C1, C2 depends on the initial condition and can be written like this using the sum of angle formula. This becomes sine, some amplitude here, some amplitude A sine. So this whole thing can be rewritten as this A sine this guy plus a phase shift. Okay, and A is both this A and phi depends on C1 and C2. Okay, so actually A is equal to square root of C1 square plus C2 square. Phi is going to be equal to which one divided by which sine sine phi. Okay, it's arctangent of C1 over C2. Okay, or arctangent of C1 over C2 plus pi. So this is basically just combining the two sinusoids together. I'm going to run out of time to explain this, to derive this again, but it's the sum of, is you expand this guy, sine A cosine B plus sine A cosine B plus cosine A sine B. Yeah. Okay.
Professor, can you move it down a little bit? It's out of frame.
Move it down like this.
Yes.
Is it okay now? Okay. So what does this look like? This is going to look like it is a sinusoid with amplitude A, but the amplitude is actually get modulated by this, right? It's A e to the power lambda t. So it's a sinusoid, and then you just keep going like this. And this envelope here, the envelope here is e to the power minus t, lambda t. So those are the three cases. Okay, so I have 8 minutes left. Kind of intentional to save a little bit of time to ask for some feedback. Is this class really hard?
Kind of.
Okay.
I think it was just the online environment that made it a bit harder.
Okay. The online environment hurts. Okay.
Professor, I have a question.
Yeah.
Will we know our final grade before we take the final next week?
What do you mean?
Like, are we able to find out what our grade is right now?
Yeah. You just send me an email.
I'll just email you. Okay.
Yeah. Is it using this paper is better than using the whiteboard?
Yeah, it's a
Yeah,
little bit better.
much better.
Yeah.
Much better.
Okay.
Yeah, it's a lot easier to see this way.
'Cause the webcams on computers aren't usually the greatest, so the phone is usually much better.
Yeah, I probably should have used this earlier, but I didn't use it until when things break down on the other one, because the connection is getting worse and worse to the extent that people cannot. Oh, you guys experience a lot of that. Once in a while, I have to wait, right?
Yeah.
So I finally just, did I show you this? This is my, did you see the setup?
Also, if need be, like if it
Beautiful.
doesn't, like, quality gets terrible and doesn't improve, then you can always just like take a photo of it and then put it on canvas with the phone itself.
So this is just my phone.
Uh,
This is my phone is a document camera.
back to your question, Tong. I don't think this class is necessarily like super difficult in terms of like math. Like I felt like I had more of a challenge with like calculus and stuff. But relating this to actual real life ideas is where I'm struggling to understand like how this correlates with anything in like the real world.
So would it be better if it is much more? We just talk a lot more about application.
Talk or do?
Do
Yeah.
okay. So you would
Because
prefer
like the
to
dampening stuff is cool. You showing us like the coronavirus, like whatever.
yeah. I did show you some of the curves, and also I actually show you a system of equations.
Yeah.
Right.
Right.
A system of equation about the coronavirus.
Because like once we start doing stuff and we're doing it, and then we have a test, like everything on test one, like I'm pretty sure if I retook it again, I wouldn't be able to do it. I would have to go back to my notes, relearn it, and then apply it again.
Okay. Sorry, okay, so you are saying that just do some basic of the technique stuff, and then just solve more real life problem.
Yeah.
So it looks like in 4, we are going to do online again. I don't know whether you get the notification, but I think
Yeah, we just got the email.
you just got the email. So maybe this class has the project has the opportunity for just essentially instead of doing a regular like assessment like test and final exam, maybe just a lot of projects.
I feel like it was kind of like difficult to start learning new material when we started moving online because with like just like the connection breaking, which isn't like anyone's fault that everyone's getting used to, it's just like harder to I feel like learn the material.
So you feel
Yeah.
that, Sylvia, you feel that, for example, even if I do this right with the paper, then you can see better. It's still not. It still have the problem.
Yeah, it's just such like a different level of like engagement that I don't think anyone prepared for. That it's like even like when you ask questions and I feel like maybe like not everyone's like prepared to answer yet. It's a lot easier to like read a room that's in person. So like moving online, it's just I don't even know how to like explain it. It's just been really hard to like absorb information.
Yeah. For
Another thing
example,
that
when I ask you guys, is it okay or like do you guys understand? And I have really hard for me to tell. In class, I can see people puzzle, right? See their facial expression.
I will say that like during the transition to now being online, I do find it a little bit harder to concentrate, I guess, because the classroom setting and being at Kenyatta is a little bit more sterilized. That there's less to be distracted with, and you're more focused per se. At least for me.
Okay.
While I agree with everyone, I do think that moving online has its benefits because now we have video recordings. If we don't understand anything in class, we can always go back and read it or watch it another time, which I think is really helpful.
Yeah,
Sure.
that helps.
Thanks to Hans for doing that for us.
Thanks, Hans.
Sure, if
It's in
Hans
the
is-
abyss.
No, I don't see him listed anywhere.
Nice.
So video, for example, if next semester, when I teach this again, I don't have the video, but I will just put whatever I write. I will try to write a little bit better, a little bit more organized, and then just take the PDF and then post it online.
Yeah, that would work. That would work good.
That will be nearly as good as the video.
Perhaps even better because I mean the PDF's usually going to be more clear.
Okay.
I think it's
Professor-
still helpful to have like a synchronous meeting where you go over the material, but I think having some notes that you can look back on from lectures would also be helpful.
Yeah, I will be. It will be synchronous. I mean, I'm kind of a synchronous person because, I mean, I just cannot imagine. I cannot imagine. I just post some stuff. I mean, then I don't really have to do anything. I mean, I basically do it for one semester. I'm just keep posting the same stuff. I mean, then I can just go on vacation.
Professor?
Yes.
So I asked this of like every professor too, but in terms of like studying priorities and things like that, is there any particular subject, since you've written the exam now, that you would say is probably not worth our time to study and to like focus more on something else rather than that? Is there a particular subject?
I can't think of it right out of my head because I actually make the test several weeks ago. So, yeah, but my comment to my response to that is that the study guide is the best way to study. Those questions I put in there.
All right.
Okay, so this class is very recipe oriented with all these different techniques. One of the reasons I don't go through that many because the book actually have a lot of examples for application. I kind of feel that if I spend too much time on that, I don't have enough time to cover this stuff. So based on Kevin's response feedback, it will be good to do more applications. Is it? So other people feel the same way?
Yeah, that would be helpful.
I also feel like because the class is like the material is really procedural, I think like when it's been written on like a board on a piece of paper and it's like fragmented because it's such like a long procedure, it would help like in the future, like what you said about posting online, that like you can maybe like scroll through it because it's so like long in a way, like the work.
Okay. So when you mean when if so you're saying that it's helpful if I post this online.
Yeah, like the physical
Is
notes.
that, yeah, the physical notes, yeah.
Or if you can ask Kenyatta for like a tablet or something that can convert to PDF as well.
Yeah, I'm thinking about that, but I haven't really decided what would be the best because I mean I probably have to try it out, but the tablets sometimes they are very small. So I mean I have looked online for some of them, so they are too small. But maybe get an iPad or something. iPad is pretty big, right? What's the biggest size iPad? Do you guys know?
12 inches, I think, something like that. Or maybe it's even bigger. I don't know.
12 inches will be probably about the same size as the page. Yeah.
Depends if you want the Pro. Obviously, it's a giant thing. I think Shannon has one there. I'm not sure if she's here.
She has a big iPad. Okay.
Yeah,
Yeah, the iPads. I think the advantage of the iPad is that whatever I put in there, then it's just a record, right?
Yeah.
Then it's much easier to post that. Because this one I can post it, but I probably have to take pictures of this, convert it to PDF.
I mean, there are bigger pads of paper that you can get if you want to get like large pieces of like, if you get like a drawn pad or something. But I don't know if that's something that would necessarily be all that helpful, or if it would just be easier to do it on like an iPad format. I don't really know.
Yeah, the bigger piece of paper is not going to help too much because I still have to. I mean, I like writing on paper, and I don't have a lot of experience writing on using the stylus thing, and I don't know how efficient I will be. Because on the paper I can be very efficient. On the whiteboard and paper I can write really fast, as you can probably know. But on the iPad, I'm
Yeah, I
concerned.
think so. No, I think you'll transition pretty well to the iPad.
Okay. So any other thing you guys want to tell me before we sign off?
Thank you very much for being willing to continue teaching online. We really appreciate how flexible and how much work you put into moving everything online.
Yeah,
Thank you.
agreed.
Yeah, I think the students are helping for like recording the stuff because I don't have enough bandwidth to try to figure out the recording and posting and all this stuff. Okay, in that case, I will be on the day of the final, just in case you need to ask me to clarify some stuff. Okay. Okay. Otherwise, I'll see you. And for those who are transferring next semester, good luck on your next journey. And feel free to drop me a note telling me where you are going. Okay.
Thank you, Professor.
Okay.
Professor.
Thank you, Tom.
Thank you, Professor.
Okay. Thank you.
That's
Bye-bye.
Bye.
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 Professor.
Bye.
Bye.
Thank you, Professor, for a great semester.
Bye. Thank you.